We're going to move on to our next section in our energy unit, and that's going to be a look at waves. So go ahead and set your notebook up for waves notes. Make sure you have big ideas on the left and tell me more's on the right, and we'll get started. It's important to remember that waves are the traveling and transmission of energy. We often think of waves as this here, where we have water waves, but it's also important to remember that there are a lot of different types of waves out there. So for example, this picture and this picture are examples of electromagnetic waves, light waves, radio waves here. And this picture here is an image taken after the 1964 earthquake showing the movement of seismic waves through the earth. So lots of different types of waves out there. We're going to look at a few different types today. So officially, a wave is a disturbance that moves through matter or space. There's a couple main categories of waves. You can have a mechanical wave that requires a medium to travel through. That's something to move through, like air or water. Or you can have an electromagnetic wave. And electromagnetic waves can travel through a medium, but also through empty space. And we'll get to those later. What we're going to talk about first is mostly related to mechanical waves, but have some application to electromagnetic waves as well. First thing is to remember that in a mechanical wave, it is the energy that's moving and not the matter itself. So the matter is disturbed, so you see, say, a ripple in the water, but the water is not moving anywhere. So when a disturbance causes a wave, such as a rock being dropped in the water, the energy is actually being transferred from one molecule to another, disturbing those molecules as it passes. It's the energy, though, that's being transferred and not the matter itself. So we're going to look at the two main forms of waves. So we're not looking at mechanical versus electromagnetic anymore. We're looking at the forms of waves and how they travel. So first one is a transverse wave, and this one is probably the most familiar in that it would look like a wave to you. And that's because when a transverse wave travels, if this is the direction of the energy that's traveling, say the rock is dropped over here, the energy is traveling away from it, the medium, what it's traveling through, moves at right angles to the direction of the energy, forming, in this case, in our water case, ripples. So we see those ripples because the molecules are moving at right angles to the direction. Couple things that are indicative of a transverse wave are the parts here, crest and trough, or crest and trough. And crest would be your high point, the crest of a wave, and the trough is your low point, the low point of the wave. The second form a wave might take is as a compressional wave. Sometimes it's called a longitudinal wave. It's the same thing, it's just a different name. The difference between a compressional wave and a transverse wave is that where in a transverse wave the molecules move at right angles, in a compressional wave the molecules move with the energy. They're parallel to it. And so in this example here, you also often see a transverse wave, or excuse me, a compressional wave drawn like this, like sort of like a slinky. The energy is moving this way, and the molecules of the medium are being squeezed as it travels, squeezed as it travels, squeezed. So you end up with two parts of the wave. First, the compression, and that's where the molecules are squeezed tight together. And second, the rarefaction, and that's opposite of a compression. It's where the molecules are really far apart. So as a compressional wave travels, it squeezes the molecules in one section, and on other sections they're really spread apart. This is how a sound wave travels, which we'll get to a little bit later. The next few slides are going to be looking at the four major properties of all waves. So this happens with a compressional wave as well as a transverse wave. The first property we're going to look at is wavelength. It's exactly what it sounds like. It's how long the wave is. It's a distance. It's measured in meters. So the way we measure a wavelength of a wave, because it can be kind of hard to tell where does it start and where does it end, is we pick two adjacent parts. So here in this transverse wave, I would pick the two crests that are closest together. In this compressional wave, I would pick these two compressions that are closest together, and I would measure the distance between them, and that would give me the wavelength. The second property that we're going to look at is frequency. Frequency is how often a wave occurs. If you do something frequently, you do it often, like I go to the library frequently. So a frequency of a wave is the same thing. How often does it occur? We measure the frequency by counting how many waves or how many parts of a wave pass a point every second. So I might be in this transverse wave, I might be counting the number of crests that pass a point every second, and that's going to give me the frequency. The units for frequency is hertz. It's a person's name, so it's spelled like this, and it's abbreviated capital H lowercase z. So if you look at these two waves, you can see that this is a high frequency wave. If I was to count the number of crests that occur every second, this one would occur much more frequently than this one. So here we have high frequency versus low frequency wave. The next property is called the amplitude. And this is all about how big the wave is. It's directly related to how much energy is put into the wave. So the initial cause of the wave, if it had a lot of energy, you're going to end up with a higher amplitude wave. If it had a little bit of energy, you're going to end up with a lower amplitude wave. So in a transverse wave here, you would measure the height or the depth. So it's the distance from the resting point to the top of the crest or the bottom of the trough. And in a compressional wave, you're measuring the density of the compression. It's how compressed the molecules are. It's going to be a little more difficult to measure. And the final of the four main properties of waves that we're going to measure is wave speed. And wave speed is directly related to the wavelength and the frequency of the wave itself. So you can look at it in a mathematical arrangement, and that wave speed, wavelength, and frequency are related in this formula, where wave speed equals the wavelength times the frequency. Wave speed in general is basically how fast it's traveling, so how many wavelengths pass a point in a given second. So if you want to measure, mathematically, if you want to measure the speed of a wave, you simply take the frequency and multiply it by the wavelength. So here I had a wave with a frequency of 3 hertz and a wavelength of half a meter, 0.5 meters. If I multiply those together, I get 1.5 meters per second. So this wave is traveling 1.5 meters every second. The last thing we're going to look at in this lecture is how waves interact both with each other waves, and with their surroundings. We're mostly going to focus first on how waves react with their surroundings. So what do they do if they encounter something in their environment? And the first thing is that if a wave hits a surface, it's going to bounce off. So if it can't travel through it, if a wave hits a surface and it can't travel through it, it's going to bounce off, or it's going to be reflected. The cool thing about the reflection of waves is they actually follow this very important rule. It's actually called the law of reflection. So when a wave hits a surface that it can't go through, it's reflected at the exact same angle that it came in at. And this is the law of reflection. It happens for any type of wave. We actually see our reflection in a mirror because the light waves are reflected to our eyes. So in this case here, this is the light wave coming in, and it's reflected at the same angle that it comes in at, following the law of reflection. So bouncing off a barrier that it can't go through. The next interaction a wave might have is called refraction. Refraction is when a wave encounters a different medium. So the most common and most familiar example of this is a light wave traveling from air to a different surface. Let's say that this is a light wave here, and it's in air, and then it hits water. So you can see this sort of bluer color is water. If the light wave comes in at an angle, part of the wave hits the water first before the other part. And when it does that, it actually changes the speed. Light travels faster through air than it does through water. So when this part of the light wave hits the water first, it actually slows down. And this wave, this light wave, or this part of the light wave hits it, and it's still going faster. So what happens is it slows down. It almost is like it's slamming on its brakes on one side and causes it to go and change direction or bend. You often see this when looking in water, especially if you're in kind of calm water. Maybe if you're fishing or something, you might see that when your fishing line enters the water, it appears to bend at the point where it hits the water. You also might notice that when you look at something in the water, it appears to be at a different place than you thought. And that's because the light is refracted. The last interaction that we're going to have when a wave encounters something in its environment is called diffraction. Kind of confusing words, reflection, refraction, diffraction, but make sure you write those down and keep them separate. Refraction happens when a wave bends around a barrier it encounters. I love this picture, and what it is an aerial photograph of water waves coming in, and it hits these two rocks and squeezes between them. And when it does, the water waves bend as they're squeezing through that, and that's called diffraction. We know that this occurs, for example, if you have someone, say, talking in another room and you can hear them through an open door. That's because the waves are diffracted as they come through the door and bend around instead of just heading in a straight line through there. The last thing we're going to talk about today is what happens when a wave encounters itself, another wave. And one thing that can happen is a standing wave can form. This happens when a wave travels out, reflects off a surface, and encounters itself. So one wave's coming out, the other wave's coming back, and they encounter themselves. If the waves are traveling at the same frequency, they're going to form what's called a standing wave. A standing wave lines up so that the wave itself appears to be standing still. This is a drawing of what a standing wave might look like, and you have one wave encountering another wave. And you can see here that the crests and the troughs have lined up in such a way that they're across from each other. These are, in a standing wave, are called antinodes, where the point where the waves cross each other is called a node. You can see here that if this line represents resting, that the wave here is at 0 amplitude and here is at the maximum amplitude. This is an actual photograph of a string being set up as a standing wave. You can see again the antinodes and the nodes as the waves interact with each other.